We'll see more examples in the exercise sessions. Perhaps what I'm going to be saying next is what you would expect to see given everything else that we've seen so far, the same type of progression. Continuity behaves actually excessively well with respect to elementary operation on functions. Let A be a subset of R, F and G be functions from A to R, C an element of A, and alpha is some constant. If F and G are continuous at C, then F plus G, F times G, alpha times F are continuous at C, and the quotient F over G, or F divided by G, is continuous at C as well, if G at X not equal to 0 for every X. In practice, this would really be true as long as G at X is not equal to 0 over some neighborhood of the point C. But specifically here, the statement of this result requires this to be true for every X in the domain A. Proof-wise, like, look, if C is not a limit point, there's nothing to prove, because continuity is automatically assured. If it is a limit point, then continuity of the functions f and g mean the limit of f when x goes to c is the limit of f when x goes to c is f at c, and the limit of g when x goes to c would be g at c. Then we can just use the theorem on the properties of limits. We have limit when x goes to c of f plus g at x. That would be the limit when x goes to c at x plus g at x. Would be the limit when x goes to c at x plus the limit when x goes to c g at x, which is f at c plus g at c. Another way to write the function f plus g at c. And literally the same type of argument proves the continuity of all these other. We've done this enough by now that I don't want to waste too much of our time writing it down, but you should be able to build the argument. A corollary to this result, if you replace the sentence continuous at C with continuous over a set A, theorem is still valid. We like continuity. Continuity behaves as it should. It does good things. We've seen some examples, and though that's not what we highlighted when we talked about them, that show that constants and the identity function are continuous. And what we get out of this is that polynomial functions must be continuous. That's a direct consequence of Theorem 30. If polynomials are continuous, then so are rational functions. Quotient of polynomials over their domain where they're well defined. Perhaps the last interesting result for this section, that the composition of two functions is also continuous. What is the composition of two functions? If f goes from a to b and g goes from b to c, then the composition g composed with f, g circle f, is a function from a c, which is defined as follows. Every x is associated to g of f at x. This is well defined because x is in a, f takes something in a and outputs something in b, so f at x in b, and g of something in b is in c. So yeah, okay, this makes sense. Theorem 31. Composition of continuous function. Assume that a and b subsets of R. F is a function from A to R. G is a function from B to R. C is some point in the set A. Well, if F is continuous at C, I'll remind you, is an A, and G is continuous at F at C, f at c is in the image of A by F, so f at A, and if furthermore this image f at A is contained in B, then the composition G equals with F from A to R is continuous C. Proof is actually fairly straightforward. Pick some epsilon greater than 0. We need to show that G f at x minus G f at c will eventually be smaller than epsilon whenever x minus c is smaller than delta epsilon x is in A. So I give you an epsilon greater than 0, you will find a delta epsilon greater than 0 that satisfies this. This is what we want. Well, what do we have at our disposal? We know that G is continuous at f at c. That's one of the hypotheses. So for that epsilon greater than 0 than we had at the start of the proof, we know that there exists a delta epsilon such that G at y minus G at f at c is less than epsilon whenever y minus f at c is smaller than delta epsilon. Now remember here, f at c, if I had been clever, I would have called this D. And I would have said, I know that G is continuous at D, not f at c, even though it's the same thing, I would have called it D. And then I'm going to use y as the name of my variable for G, even though I might use x, but let me just call it y for now. And I would have just talked about the continuity of G in terms of the variable y at the point D. But this is exactly what you would have found if you had done that. So that's just applying the definition of continuity of the function G at any point in its domain, in particular f at c. Now this is true whenever, of course, y is in the domain of the function G. Remind you that G goes from B to R, so this is true for any y in B that satisfies this. Now we also know that f is continuous C, that's part of the assumption. So there exists a eta which will depend on the delta epsilon that I found here, which itself depends on the epsilon, such that f at x minus f at c is smaller than delta epsilon whenever x minus c is smaller than this eta delta epsilon and x belongs to A. Now, let me remind you, this we're basically calling y. Here, this is what we had called D, or highlighted as D. Well, we have all the information we need then, because G at f at x, I replace I by y by f at x here, minus G at f at c will be smaller than epsilon whenever x minus c is smaller than n delta epsilon. X belongs to. Go back one slide. The delta epsilon that I want is the n delta epsilon. This will give me exactly what I want. This is just learning how to manipulate the definitions. There isn't an awful lot of thinking going on. And as before, the same result holds if you replace continuous at C with continuous over some set A. Let's end this section with an example and a remark. Consider the following function. Every x, it sends the square root of 3x cubed plus x plus 1. It is continuous at c equals 7. Why? Well, we know that 3x cubed plus x plus 1, what's going to play the role of f at x, is continuous. It's a polynomial, so it's continuous at c equals 7. And the square root function is also continuous. So I have composed here two functions which are continuous. I call this f at x, but it's not f at x. Let me call this perhaps h at x. So f at x is the square root of h at x, where h is continuous, and if you want, I can rewrite it as g h at x, where g at y is the square root of y. Now, we would have to show that this function is continuous. That's an interesting exercise. But if you're shown that this function is continuous, then this composition here has to be continuous at c equals 7. This is going to work very well as long as what you have inside is not negative. Finally, I'm going to mention that algebraic functions can be obtained from rational functions with the help of roots. So basically, allow fractional powers in your rational function, either inside or outside, because you can show that fractional powers are also continuous, then algebraic functions are going to be continuous on their domain as well. It's also true for trigonometric functions, exponential functions, logarithmic functions, and other interesting transcendental functions.